Alrighty, so this is kind of the review session, so we can talk about whatever you'd like to talk about leading up to the midterm review, or leading up to the midterm, which I believe covers chapters 1, 2, and 3. So is there a specific chapter that you'd like to talk about, or do you want me to just kind of do some problems from the chapters and like work through them, like in general?
I think just like a general view for me would be great, Olivia. Thanks.
Awesome, okay. So let's start with the review in chapter 1. And this is on page 78. And so chapter 1 was talking a lot about like functions and change. So I would look through the chapter summary to make sure you understand what all of those like terms like end up meaning. Let's do problems 4 and 6. So I'll give you some time just to kind of sketch out what you think these functions look like on your own. And in a couple minutes, we'll get back together and compare answers. Okay. If you guys are ready, I'll just start going over what I've got for these problems. First thing to do is determine what your x-axis is and your y-axis. So this is sketching temperature as a function of time. So this is time and this is temperature. So our high temperatures are going to be up here and our low temperatures are going to be down here. Then it warmed up throughout the morning and suddenly got much cooler around noon. So we're going to call this 12 o'clock. So it warmed up all morning and then it got much cooler at noon. When a storm came through, and after the storm, it warmed up before cooling off. So this is going to be, I don't know, this is going to be about 7 p.m. at sunset. So this is kind of what this graph looks like. Is that kind of what you guys had? You can just like put something in the chat box or not, it's fine. Okay, so then for number 6, it's the same kind of thing. You have distance from Kalamazoo as a function of time, so d of t. So this is the distance from Kalamazoo, and this is the time. When you are passing through Kalamazoo, the distance from Kalamazoo is going to be 0. So this is at Kalamazoo. And this happens at, we don't really know what time exactly.
I'll have to Google it and look at it later.
What was that?
She's the one who put it on there.
Okay. So, okay. So, then you drive at a constant speed from Chicago to Detroit, a distance of 275 miles. About 120 miles from Chicago, you pass through Kalamazoo, Michigan. Sketch a graph of your distance from Kalamazoo as a function of time. So you are closer to when you're in Kalamazoo, you're about 120 miles from Chicago and what, 155 miles from Detroit. So this is going to be when you're at Chicago, and this is at Detroit. And I'm just kind of labeling these points not with numbers, but like just like as notation so that I know how I'm going to be drawing this. Oh, and that's going to be like that. Something like this. Okay, so that is kind of just like a review of how to like think about linear functions based upon like a paragraph that they'll give you talking about just kind of, you know, whatever they want to talk to you about. Okay, let's try problem 12. So this is page 79. Here we are going to be matching linear equations with the graphs that are just below. So we have A, B, C, D, E, and F. All right, what do you guys think about A? So the equation here is y is equal to x minus 5. First thing I would look for is to see what the y-intercept is. If you remember from y is equal to mx plus b, this is your slope, m, and this is your y-intercept. So your y-intercept here is going to be -5. So I'm going to immediately look through and try to find something with y-intercept that is negative. The only ones that stand out to me right now are 5 or 6. So I know it has to be one of those two because they have the negative y-intercepts. Then I'm going to look at slope. My slope for this is 1, and it's positive. So I have a positive slope. It looks like 6 is a negative slope, and 5 is a positive one. So I'm going to go with 5 for A. If you guys have anything you just want to put in the chat box, all of your guesses, that's fine by me. And tell me if this is not something that you guys want to talk about. I just kind of wanted to go through and cover as much as I could. So for B, we have y is equal to -3x plus 4. So we know our slope is going to be -3, which is negative, and our y-intercept is going to be 4, which is positive. Ones with positive y-intercepts and positive slopes, and negative slopes, excuse me, the only one there is 4. And so I would go through and do all of these in this exact same way, ask what the slope is, what the y-intercept is, and look at the graph and try to figure out which graph is consistent with that. For C, we just have y is equal to 5. So y is equal to 5 at all times, regardless of what x is equal to. So the answer is going to be 1. For D, y is equal to -4x minus 5. So m is -5, and the y-intercept is -4, excuse me. And the y-intercept is -5. Both of these are negative. There we can go back up to here where we know we have the negative slope, negative y-intercept. So this is going to be 6. E, positive y-int, positive slope, looks to me like it'll be 2. And finally f, which is, so my y-intercept is equal to 0, and my slope is equal to 1/2. So it won't be as steep, and it'll cross at 0, 0. So this will be 3. Okay. Oops. All right. So, let's do 48 then. If you guys remember this is on page 82, by the way. This is kind of like the exponents that we were working with at the beginning of the semester. So we have the exponential function p is equal to e to the 0.08t, and we have the function q is equal to e to the negative 0.3t. And so we want and we just want them in these forms. So we have a flat number to the t. Does anyone remember how to do this? Okay, so basically we have 2 equations for working with exponentials. We have p, sorry, I'm writing this corner. I have my chat box in this big empty space here, which is why I never write in that area. So we have p is equal to e to the kt, and p is equal to a to the t. So basically, a is equal to e to the k. Does that make sense? Because what we can do is we can put these together. If p is equal to both of them, what we can say is that this is also equal to a to the t. We can just forget about the p. So we have e to the kt is equal to a to the t. If we wanted to solve it out, we would take the natural log of both sides. So we would end up with kt natural log e is equal to t natural log a. And this is going to help us find what k is, because we know that is equal to 1. So kt is equal to t ln a. We can divide both by t. So k is going to be equal to the natural log of a. So we have all of this that we know. We know that e to the ln a t works. And we know that, so that we know how to find k. Which may not be very useful in this instance because we already have k. And we can also say that if e to the kt is equal to a to the t, then e to the k is equal to a. So these 2 things are what we're going to be focusing on. I don't actually have a calculator near me. Sorry, I just got back to campus this morning. So if somebody wants to plug this into their calculator, that would be great. But P is going to be equal to e to the 0.08. So this is a number to the t. Correct? I think that's right. Give me a sec. Yeah, that should be right. Yep. Okay, so P is equal to 1.083 to the T. So A is equal to 1.083. And so if we were to take the natural log of A, it should be 0.08. And that's how we can check our answer. So if somebody wants to do that, you can. I'm going to trust that this is right. So we're going to do the exact same thing with Q. We have Q is going to be equal to e to the negative 0.3 to the t. So this is some number to the t. And we could go through the calculator, but I don't have one right now to find out what that is. Okay. So that kind of just is like a refresher on like what these equations are kind of generally doing. Let's now try to do, let's do problem 50. So you need $10,000 in your account 3 years from now. So I'm going to start writing down what I know this is going to be an exponential problem just by the nature of what we're like working with right now. So I'm going to say I know that P is equal to A to the T, and I know that that is also equal to E to the KT. I'll figure out as I go what things are what. Oh, excuse me, this is P not A to the T and P not E to the KT. So this is the original amount in the account, this P naught, and this is at the end of time t. So I'm going to start defining what these things are. P, I know that I need $10,000 at the end of the time, so P is going to be equal to 10,000. I know that time is going to be 3 years. And the interest rate is going to be $8 per, or 8% per year, compounded continuously. So how much should you deposit now? That indicates that I'm going to want to use this one because I know I can write an interest rate as this. This being the percentage, 8%. This is the original sum, and because I'm adding the 8% to it, it's growing. So every time t gets bigger, this gets bigger, so my principal amount gets larger, and at the end, my p is larger. If I was losing 8% per year, it would be this, because then it would be getting smaller over time. Does that make sense? Notice that this interest rate is not K. So if Just like it, like sometimes it's like a gut reaction to say, oh, that should be K, but the interest rate is not going to be K. You're going to just relate it directly to how much money you originally have. So I'm going to fill in what I have right now. I have, excuse me, 10,000 is equal to P naught times 1.08 to the 3. So what I would do is I would divide this by 1.08 to the 3, divide both sides by that. And so I end up with P naught is equal to 10,000 divided by 1.08 to the 3. Okay, this is some number. Again, don't have a calculator, can't tell you exactly what that number is. If somebody finds it, you can go ahead and put it in the chat and I'll put it up on the board. But notice this number is going to be smaller than 10,000. And that is because the money is growing over time. So P naught is equal to 7,938.32. So if you get 8% per year and you put $7,938 into your bank account, in 3 years, you'll have $10,000.
So Olivia, on the midterm, we're not going to be able to use a calculator. I guess it would just be, the answers would just sort of make sense at that point?
Yes. You probably won't have problems specifically like this that have this form. It's just very important that you guys can manipulate these two equations here. Because as we'll do in just a second, we're going to find something, we're going to use e to the kt. And this is probably what's going to be on your midterm, more likely than not, rather than the a to the t. And the reason is because this gives you numbers, big old numbers, and this you can write in terms of natural logs. So if I have the natural log of 2, I can just leave it as the natural log of 2. There's no need for me to simplify that any further. Okay. So, even if you don't have, just going somewhere with the sentence, but I forgot where I was going with it. If you don't have a calculator, like you won't on the midterm, you can't solve this problem using e to the k without a calculator, but they won't give you problems that are exactly like this. Okay. So let's take a look at all right, let's do 53. I think we can use e to the kt for this. So we have this equation. And in this case, the P is going to represent populations because we're dealing with bacteria. The size of an exponentially growing bacterial colony doubles in 5 hours. How long will it take for the number of bacteria to triple? So we're given some starting information. So our starting information looks like this. 2P naught is equal to P naught e to the k. Or the 8k2. I'm going to erase that and write it better so it's legible. Because this is 2 hours. 5 hours. I read the problem wrong. 5 hours. All right, so, and this is double the original. So I'm going to divide both sides by P naught. So I can get that variable out of the way. So I have 2 is equal to e to the 5k. How am I going to solve this? What I want from this problem, time for it to go to 3 p naught is equal to p naught e to the k t. So what is stopping me from solving this problem? If I were to attempt to solve this problem, I would say I have, I'm going to divide both sides by p naught. Now I have 3 is equal to e to the k t. I need to find t, but I can't do that without knowing k. And I know that k is a constant. So if I use this information to help me find k, I can solve this problem. So I'm going to take the natural log of both sides. So here I have natural log of 2. And knowing our log rules, these exponents are going to come down outside the logarithm. So it'll be 5k natural log of e, and this is equal to 1. So the natural log of 2 is equal to 5k divided by 5 on both sides. K is going to be equal to natural log of 2 over 5. And this is as simplified as k is going to get. And so we're just going to put that right here. And continue solving this. 3 is equal to e to the ln 2 over 5 t. And again, natural log both sides. So the natural log of 3 is equal to the natural log of 2 over 5 times t times the natural log of e, which is equal to 1. So it's basically from here just a big old simplification game. Natural log of 3 is equal to natural log 2t, or 2 times t over 5. Don't accidentally end up with that t inside the natural log. Times 5 on both sides. 5 ln 3 is equal to t ln 2 divided by ln 2. So the time for tripling is equal to 5 natural log 3 over natural log 2. Is there a rule that we have to simplify this? Yes, no, maybe so. This goes back to our basic natural log rules. That's dealing with doubling time. Where are our natural logarithm rules? Sorry, I'm just going to make sure that I do it right. So, okay, so we are going to look at dividing. Is there a logarithm rule that we can use here? The answer is no. The logarithm rule is specifically if we have the natural log of a over b, this is equal to the natural log a minus the natural log b. So if we were subtracting natural logs, we could simplify it into something else like that. But because we're dividing these natural logs, we can't. So this is our final answer. And this is a perfectly acceptable way for an answer to look in a problem like this. Okay, give me just a sec. My computer is about to die, so I'm going to plug it in. Before it does that. Maybe. All right, give me a sec. Okay, cool. We're back online. Is everybody okay with this using e to the kt and having answers that have logarithms in them? Can you guys hear me? Cool.
Yep, I can hear you.
Awesome. Okay. Thoughts? I think one of the big things that they'd like to test you on from chapter 1 is going to be this exponential stuff. So if there was one thing I'd tell you to study from chapter 1, it would be exponential stuff. Okay, let's talk about chapter 2. Again, if anyone has any specific questions, stop me and we will go over them. All right, this is going to be on page 125. All right, let's start with five. So we're given this function that looks something like this. And we're given points on this function. All right, so the question is, at which of the labeled points is the derivative going to be positive, negative, and 0? And at which of the labeled points is the derivative going to be largest? And at which of the labeled points is it going to be the most negative? All right, let's start this off. We're going to color code this for easy stuff. So this is going to be positive. So anything that is a positive derivative, we're going to mark in red. Negative will be in blue, and 0 in green. All right, so you can start listing stuff in the chat box where things are positive, negative, 0. Throw any thoughts you have into there. C and G are positive. Yep. No other positive ones. B, D, and F are 0. And our negative ones are going to be what's left, which is A and D. All right. So which of the positive ones is the most positive? Which one is the greatest number? G. Yep, because this is going to be kind of a line that looks like this, and this is kind of going to be a flattish line. So G is the point at which F prime is largest. All right, what about the most negative? A. Yep, I'd agree with you there. Tangent line is going to look something like that. Here, it's going to look something a little bit more like this. So this is going to be a little bit steeper than this is. So I'm going to say A is the point at which F prime is most negative. All right, cool. You guys remember how to do that? Let's do 11. Let's do 13. Let's do 15. So I'm going to sketch out very briefly what these original functions look like. And then we're going to draw the derivative. Okay. I have the derivative of 11. What is this gonna look like? Is it gonna be a line? Is it gonna be a parabola? Well, I know because I'm looking at this. This is a first order. So the equation looks something like this. Y is equal to mx plus b. I know if I were to take y prime, this would be, the derivative would be m, right? Oh, I got a message, I think. No, I didn't. Never mind. Okay. If you guys have anything to say, feel free to just put it in the chat box. So y prime is going to be equal to m. I'm looking at this. My slope here is negative. So I'm going to say, actually, there are numbers here, so we could find out what the actual slope is, I think. That's 3, and this is 2. So my delta y over delta x, delta y is going to be -3, delta x is going to be +2, so my slope is going to be -3 over 2. So I'm going to draw a line right here at y is equal to -3 over 2. And that's my derivative graph. Cool. Now I have this parabola. What do I know about taking the derivative of a parabola? Well, this, we're going to call this g. This looks something like this. And I know that if I take the derivative of this, I'm going to end up with y is equal to 2x. So I know I'm going to be looking for a line. And I know that this is where g prime is equal to 0. And that point is going to be 2. So here at 2, g prime is going to be equal to 0. It's going to be g prime is positive here, and g prime is negative here. So it'll look something like this. Okay. You guys might not have seen a function that looks specifically like this before. But what this is a, what do you call it? Quartic function. This is y is equal to x to the 4th. Easy way to just kind of like look at this is say if they're going in both the same direction, like this is both has things going infinity to up, this also has 2 things going infinitely up, then it's going to be an even number. So this is x squared, this is x to the 4th, x to the 3rd is going to look something like this, where something is going up and something is going down, and that's characteristic of an odd function. So this is y x to the 3rd. So if we end up with y is equal to x to the 4th, then what we're going to do is y prime is going to be equal to 4x to the 3rd. So our derivative, we know, is going to look like a cubic function. So let's draw it. Where is the derivative equal to 0? This is here, here, and here. So, let's draw. This is at 0. This is, there's this line here. It doesn't explicitly say what that is, but it's just after that line and just after this line. So this is where it equals 0. And then here, I'm going to just label the areas where it's positive and negative. So here it's positive. So it's going to be up here somewhere. Here it's positive, up here somewhere. Here it is negative. So it's going to be down here somewhere. And here it's negative, so it's down here somewhere. So what it's going to look like is, we're just going to kind of connect these pieces. And we know it's kind of cubic because it's one end is going off into negative infinity and one end is going off into positive infinity. Does that make sense? Is that kind of connecting what you guys were learning about taking the derivative of like a number versus how to find the derivative using a graph? Anybody? Okay, I'm going to assume that's okay. Alrighty. Let's take a look at problem 35. Oops, the wrong kind of graph. So we have this, and a space on my tablet. Okay, so we have all of these points, and we're trying to find where both dy dx and d squared y dx are positive. So, just a refresher, this is a different notation for y prime, or it's just like the derivative of y, and this is the second derivative. So they will use these notations interchangeably, so it's just kind of important that you be able to pick out that they are asking for the derivative and a second derivative here. So we have these points. Where is the first derivative and the second derivative both positive? Well, where is the first derivative positive? That's going down, so that's negative. This is positive. Cool. This is positive. Awesome. 0, negative. So I am mainly looking at points B and points C, points B and C. Okay. So here, basically when I look at second derivative, when I consider it, I am thinking like, how do I like go, am I going like more and more positive or less and less positive? Yep. Joshua has it right in that at point B, I'm getting more and more and more positive, and at point C, I'm getting less and less and less positive. My slope is approaching 0 as opposed to approaching the inflection point, which is right here, which is something that we talk later on. So, yeah. So point B. You're right. Okie dokies. Okay. Did you guys talked about limits pretty explicitly, right? So you talked about like limits and continuity and all that jazz. Let's look in the focus on theory about continuity. Just as a refresher, we're going to do 13 and let's do 16. So for 13, we have, oh, that's really off balance. So we have, and 16 looks like this. So this is 0.1, 0.2, 0.1, and 0.2. Okay, so we can pretty well establish that both of these functions are not continuous on the range 0 to 2. Why is that? Well, there's a break in the function. There's a point where the function like stutters out and starts again somewhere else. And so that's kind of how I think about continuity if I'm looking at a graph. And yeah, if we're only analyzing this portion though, if we're going from 0 to 0.5, then both of them are continuous. Is it really cool with this concept of continuity? You guys talked about this, right? Cool. Yeah. So just be able to tell if a function is continuous or not is what I would say. I don't think they're going to make you find derivatives by hand, but I did not write the test. So I guess I cannot say with absolute certainty that they won't, but it would seem really ridiculous if they would try to make you do that when you know how to find a derivative. But as I said, I didn't write the test. Yeah. So, sorry, man. I don't have the answers to everything. Cool. Let's talk about chapter 3. Where is key review problems? Oh, there they are. Okay, so basically chapter 3 is a lot of finding derivatives. So let's find some derivatives. My suggestion to you guys when you're trying to go through these is to literally go through, and you guys have even ones in the back of the book, right? I lied, you guys have odd ones in the back of the book. So go through and do all of the odd ones. We'll do some even ones while we're here. And make sure, just check in the back of the book to make sure they're right, and you just keep doing them until you feel comfortable that you can look at a derivative and figure out what the derivative is. So let's do 2. Let's do 6. And let's do 10. And let's do 22 and 24. Okay, so we have a list of derivatives that we're going to be finding. Let's start with number 2. We're just going to use our generic rules for this because it's x to the third minus 3x squared plus 5x. So we know we can add and subtract derivatives. So we have 3x squared minus 6x plus 5. Cool. For 6, we have the function y is...
Olivia, what page are we on?
We are page 165.
Okay.
Sorry.
Oh, that's a 6.
Yeah.
Got it.
My handwriting kind of sucks. Okay. So y is going to be equal to 5e to the negative 0.2. T. So we know that y prime is going to equal to, based upon the general rules that we learned for finding e to the kt, and based upon the chain rule, 5 times negative, and then I'm going to write it in terms of a fraction, just because that's how I like to think of decimal points. And then e to the negative 0.2 t. So this is going to simplify out to be y arrow y prime is equal to negative 1 e to the negative 0 times derivative. There we go. You guys are okay with using or finding derivatives of e to the kt, right? Sorry about that. Cool. Let's do number 10 then.
Just to review that, when you find the derivative of e to the kt, you just bring down the k.
Yep.
And you don't have to subtract one like you would normally do to find a derivative, right?
No, because e to the t is a different function than x to some number.
Right. Got it.
This k is like a different entity, which is something that you'll kind of figure out if you have if you're trying to find the derivative of so we have g is equal to 2 to the x. If you try to follow the rules that we would for x to the 2, you'll find that it doesn't work. And so it just makes it very, very awkward. Do you know what you're supposed to do in this instance? If you have something that's like x, 2 to the x?
I don't remember.
Okay. Basically, we're going to do exactly what we did with the exponents. We're going to say that 2 to the x is equal to e to the kt, or d2 to the t. I don't know why I wrote 2x. That's 4. Okay, so 2 to the t is equal to e to the kt. And if you remember, we have...
That's right.
Is equal to ln 2. So then we'll solve it using e to the kt, where k is equal to ln 2. So the derivative of 2 to the x is going to end up being ln 2 times 2 to the x, or ln 2 times e ln 2x, because these are the same. Cool. Okay. Let me get rid of some of this stuff. All right. So for number 10, we have something that we're familiar with in terms of this is x squared. But then we also have a plus 3 natural log of x. And so this is just testing to make sure you guys remember what the derivative of the natural log is going to be. Y prime is going to be equal to 2x plus 3 times, what is the derivative of a natural log of x? There we go, 1 over x, exactly. So this is times 1 over x. We're going to simplify this out so that y prime is going to equal to x plus 3 over x. And that's our derivative. Okie dokies. Like I said, just kind of do about a million of these until you feel comfortable doing them. This is 22. 22. F of x is equal to sine 2x. What are we going to do? How are we going to find this? F prime is going to be equal to, what we're going to do is kind of like we would do with like chain rule. I'm going to move that and e to the kt in that same kind of idea. We're going to say 2, and then the derivative of sine x is going to be cos 2x. So f prime is going to be 2 cos 2x. What is f double prime? F double prime, we're going to pull this 2 out again. So this is going to be 4 times, and then the derivative of cos is going to be negative sine 2x. So we have negative 4 sine 2x. All right. And let's take a look at 24. What rule are we going to use to solve this problem? Well, I see division, so my first thought is the quotient rule. And the quotient rule, we have f is going to be equal to t plus 4, f prime is equal to 1, and g is equal to t minus 4, and g prime is equal to 1. Correct? So our quotient rule is going to look something like this: f prime g minus g prime f over g squared. And I mixed that up last week, so I'm going to double check because I don't want to get it wrong again. Yep. All right, so we're good. So we are going to do f prime times g, which is just because f prime is 1, it'll be t plus 4 minus g prime times f, or t. Oh, this is minus. Don't mess up your signs. Minus 4 t plus 4 all over t minus 4 squared. So we have t minus 4 minus t minus 4. I'm just distributing that negative sign. T minus 4 squared these t's, we're going to lose the t, so this is -8 over t minus 4 squared. And that is our derivative. Everybody cool with all of this stuff so far? Okie dokies. Let's do a couple more. Let's not necessarily find the derivative for these. We can if you guys would like, but let's just take a look at 12. Let's take a look at 20. 30. The denominator for that last one is for the last problem. We just had a question in the chat. The last problem was -8 over t minus 4, and this is squared because this is g squared. Remember? F prime g minus g prime f. This is g squared. And yeah, g was equal to t minus 4, and f was equal to t plus 4. Okay. Okay. So basically what we're going to do with these problems is I'm going to write out the function, and you guys are going to try to think about how you would solve this. Like, are you guys going to use the product rule? Are you guys going to use the chain rule? Are you guys, like, how are you going to solve the function or find the derivative? So G. Feel free, if you have any thoughts about any of this as I'm writing them down, to go ahead and put it in the chat box. Okay. Does somebody have their microphone on? Maybe. That's fine. So this we have R. Oop, put the parentheses in the wrong place. Okay. Yeah. We can also do 8. Okay. Any thoughts about number 12? How are we going to solve this? Where are we going to start? First thing I see when I look at this problem is I see a function raised to the power. So I'm thinking chain rule. If you guys have a problem that you guys, I wasn't planning on doing all of these problems and finding all of these derivatives because that would just be really time consuming. I was just gonna make sure you guys knew like what methods to solve a problem with, but if you have any problems that you specifically want me to solve or that you don't get why I'm going to use this specific rule, feel free to ask us to solve them. And we just had somebody in the chat box say that we would bring down the 3, which is not entirely correct. I mean, like it is, but this is going to be equal to some function, like internally. So this is, okay, this is prime of g times g prime, right? This is what the chain rule is. So because we have g on this outside, I don't want to confuse anything. I want to say f is going to be equal to h to the 3, and h is going to be equal to z squared plus 5. And so that's how I am gonna bring this down. I am gonna say it's 3 times z squared plus 5 squared times 2z, because that's derivative of h. But I guess my first thought isn't to bring down the 3, because I don't want to forget about this 2z on the outside, because this is an important part of the derivative too. Okay. All right, what about 20? Same sort of thing. You got this 5 here. We want to use the chain rule because we've got a function, and then that function is all to the 5. All right. What about 30? Quotient rule. Exactly, because we have a function divided by another function. Big indicator of the quotient rule is if you get this big division bar here. That's like the first thing I think of. Sometimes it's not entirely correct, or you can solve it another way and it's easier, but it just is a big giveaway. Okay. What do we do with this? I can consider there to be parentheses there. Product? Is this a product? This would look like a product if it was sine t times e to, or the square root of e to the t plus 1. But this is sine of e square root of e to the t plus 1. So what this actually is we're going to use chain again, where this is our outside function and this is our inside function. So chain rule doesn't always look like an exponent on the outside and a function inside. You always have some outside function. In this case, it's sine, and an inside function. In this case, square root of e to the t plus 1. So the way you would do this is you would say that f is equal to sine, or g is going to be equal to sine h. H is equal to square root e to the t plus 1. Or h is equal to e to the t plus 1 to the half. Because that's how we think about square roots. So that's, you would end up using the chain rule for this, not the product rule. Just as a reminder, guys, we had some problems with this last semester at least, so I'm just going to say it. I don't know if you guys are having the same problem, but when you have a periodic function, there's always something after it. This is meaningless. This is meaningless. I need to have cos x or sine of 3. This is a number. But if you just have the 3 letters sin, it doesn't have any meaning to it because it's not the sign of something. So, okie dokies. What about this one? Quotient. Yep. Yeah, basically. And to find derivatives, we have our like adding and subtracting derivatives, which we know is easy as pie because it's basically just the same. Okay. Oh, and just a reminder, the k in here is a constant number, so this could be like 2 or something. It's not going to change, is basically what they're trying to say. All right, and finally, what about 8? There are 2 ways that I think that would be pretty easy to do this. Number 1 is the product rule. Number 2, honestly, you could just FOIL it. So first, inner, outer, and then last. Multiply them all together, and you'll get some sort of long polynomial. And then you could just do your adding and subtracting like that. But both will end up with the same result. The first part be the inside function. Are you talking about number 8, Katie? Yes. You can definitely use the product rule for this. So this would be the first function. Give me a second. I will erase this word. So this would be f, and this would be g. Because here there is no function within a function. If I were to try to use the chain rule here, I would say, okay, so I have to pick one of these functions to be my f and pick one of these functions to be my g. And I know that they're nested within one another if it's going to use the chain rule. So the difference between that is we have z squared plus 5, this is just what we had up there, to the third. So I can easily say that, okay, so if I have a function within a function, my outer function is going to be g cubed, and my inner function is going to be g is equal to z squared plus 5. I can rewrite this in terms of g cubed if g is equal to z squared plus 5. If I try to do that over here, I'm going to say that, okay, so I have f, and we'll call this f to start with, because I'm going to try all my options. There's no function that is acting on f. Yes. So because they're basically like 2 functions that are like multiplied together, they're not necessarily completely independent of one another, but this function is not directly like acting on this function, then I'm not going to use the chain rule. Because if I were to try to find a g, I wouldn't know what to put here. And then I wouldn't be able to use this because I wouldn't know where to put it, because they're not acting directly on one another. So that is what I use at least to think about chain rule versus product rule. Yeah, no problem. And I think I mentioned this in one of the earlier videos, but when you're looking at chain rule, there's always like 2 ways to look at it, in my opinion. You can kind of look from the inside out. So you can say, okay, so I have this function here. I'm going to start inside these parentheses. Is there any function acting on this function? This whole thing is to the third. I'm going to use chain rule. Or you can start from the outside and look in. So I have this to the third. Is there a function in here? Is this a function? Yes. I'm going to use chain rule. So whatever works for you, to consider what, like how the functions are relating to one another. If I were to try to do that either inside out or outside in method with number 8, I would say, okay, so I have this function. This is a function I see. Is there any function acting upon this? Nope. Or if this is a function, is there a function inside? My function is going to be this chunk here. This is what I'm taking the derivative of. and there's nothing that you can really simplify further, but then I'm not including this. So I have to find a way to explain my whole function, not just one piece of it. So yeah. Okay. Thoughts, comments, concerns, questions? Maybe. Okay. Well, if there are no questions, then we're probably going to wrap this up. Feel free to email me anytime. I got a bunch of emails like the day before break, and I checked my email like halfway through break and realized that I had gotten a bunch of emails and I hadn't seen them. So I'm sorry I didn't check my Canvas over break that much, but I will check my Canvas now that school is starting again. So feel free to email me or post on Canvas and like ask a question in like underneath a video or an announcement or something, or make a discussion topic, basically anything. And I am more than happy to help you guys figure out what's going on. So yeah.
Thank you, Olivia. This was a big help.
Yeah, no problem. You guys have a good day and good luck on your exam. I know you can do it.
That makes one of us. Thanks.
You got this.
Thanks very much.
I appreciate the confidence.